How can something bigger than millions of suns appear before the universe should have had time to build it? Because what James Webb found was not just early, it was so early, so heavy, and so out of place that it may be forcing astronomers to rewrite the opening chapter of cosmic history. So before we go deeper, tap like, if space mysteries pull you in, subscribe if you want more stories that make the universe feel bigger, and share this with one friend who loves asking impossible questions. For years, astronomers had a simple picture in mind. The early universe was supposed to be messy, young, and unfinished. A few 100 million years after the Big Bang, space should have been filled with small galaxies, raw gas, and the first generations of stars still trying to light up the darkness. Black holes were expected to exist too, but only as tiny beginnings, seeds, small leftovers from giant stars that had lived fast and died hard. That story felt reasonable because growth takes time. A black hole does not become supermassive in a weekend. It grows by pulling in gas, dust, and anything unlucky enough to drift too close. But this is where the problem starts. As matter falls toward a black hole, it heats up and shines with enormous energy. That light pushes outward. So the faster a black hole tries to feed, the more its own radiation fights back and slows the meal down. Astronomers call this limit the Eddington limit. You do not need the math to feel the meaning of it. Nature appears to set a speed limit on how fast a black hole can bulk up. If you start with a small black hole, even one that feeds as fast as physics normally allows, you still need a very long time to build a monster, and the early universe did not offer much time. That is why this discovery matters. It does not just break a record, it threatens the schedule. The object at the center of this story is called UHZ-1. The name sounds cold and forgettable, but what it represents is anything but ordinary. UHZ-1 is a distant galaxy seen when the universe was only about 470 million years old, roughly 3% of its current age. Its light traveled about 13.2 billion years to reach us. That alone would make it special. But the real shock is not the distance. It is what was sitting inside it. To find it, scientists needed help from an accident of cosmic geometry. Between us and UHZ-1 sits a massive galaxy cluster called Abell 2744, sometimes called Pandora's cluster. It is so heavy that its gravity bends space itself and magnifies light from objects behind it. In other words, the cluster acted like a natural zoom lens. James Webb spotted the distant galaxy through that lens. Then NASA's Chandra X-ray Observatory stared at the same region for more than 2 weeks and picked up a faint X-rays coming from the exact same place. That X-ray glow was the giveaway. X-rays like that come from incredibly hot gas falling toward a black hole. Without the lensing boost from Abell 2744, the signal likely would have been too faint to catch. But nature lined up the shot for us. And when astronomers measured the source, they realized they were looking at the most distant black hole ever detected in X-rays. Then came the number that changed the mood. Based on the X-ray brightness and energy, researchers estimated the black hole's mass at somewhere between 10 million and 100 million times the mass of our sun. Stop there for a second. This was not supposed to happen. Not so early. Not in a universe still crawling through its first 500 million years. If that mass estimate is right, UHZ-1 is not some baby black hole taking its first breath. It is already huge, already feeding, already sitting in the dark like it skipped most of the normal growth process. And the deeper shock is the ratio. In nearby galaxies today, the central black hole is usually tiny compared with the total mass of the stars around it. A common rule of thumb is that the black hole holds only about 0.1% of the stellar mass of its host galaxy. UHZ-1 does not behave like that. In UHZ-1, the black hole appears to have a mass similar to all the stars in the galaxy combined. That is a completely different picture. It is like finding a seed that weighs almost as much as the fruit around it. That image alone is enough to make astronomers pause. Because if the center became enormous before the galaxy around it had fully grown, then maybe the order of creation was not what we thought. For a long time, the usual story went like this. First comes the galaxy. Gas collects. Stars form. Some stars die and leave behind black holes. Then those black holes merge, feed, and slowly turn into giants over billions of years. But UHZ-1 whispers a more unsettling idea. Maybe in at least some cases, the black hole did not wait for the galaxy. Maybe the black hole came first, and the galaxy grew around it. That is not a small change. That would be a change in cause and effect. And once James Webb opened this door, more strange objects started stepping through it. Across Webb's deep surveys, astronomers began finding a new class of early objects that looked compact, unusually red, and oddly common. They became known as little red dots. These objects began showing up in large numbers in the young universe, especially around the era beginning roughly 600 million years after the Big Bang. They were tiny, bright, red, and deeply mysterious. At first glance, they looked like they might be active black holes. Some showed broad light features that often point to gas moving around a central monster. Some appeared too bright for their small size. Some seemed to contain black holes far too large for the galaxies hosting them. That made people nervous, because if many of these objects were truly overmassive black holes, then UHZ1 might not be a weird exception. It might be the first member of an entire population. That possibility is where the story stops being one dramatic discovery and becomes a real crisis. One impossible object can be treated as an outlier. A whole family of impossible objects is harder to ignore. And Webb kept giving astronomers reasons to worry. In 2025, researchers using Webb confirmed an actively growing supermassive black hole in a little red dot called Canix LRD Z8.6, seen just 570 million years after the Big Bang. The galaxy looked young, compact, and not especially rich in heavy elements, yet its black hole appeared larger than expected for such an early and relatively small host. Again, the same pattern. Not just early black holes, overgrown early black holes. Then the debate intensified again in 2026 with one of the most important follow-up results so far. Webb was used to study another little red dot behind Abell 2744, an object called Abell 2744, QS01. Because gravitational lensing magnified it and even produced multiple images of it, scientists could do something they had not done before at this distance. Instead of only estimating the black hole mass indirectly from bright emission lines, they actually mapped how hydrogen gas was moving around the center. What they found was startling. The gas showed clean Keplerian rotation, the kind of motion you expect when most of the mass is packed into one central object. From that motion, the team made the first direct black hole mass measurement in the early universe. The result was about 50 million solar masses, in a tiny galaxy seen roughly 700 million years after the Big Bang. That number matters on its own, but the ratio matters even more. In QS01, the black hole seems to make up about 2/3 of the galaxy's total mass. 2/3. In normal nearby galaxies, that fraction would be absurd. Here it was the measured result. Even more striking, the gas in the object appeared almost entirely made of hydrogen and helium, with very little of the heavier elements you would expect if generations of stars had already enriched the galaxy. That makes the environment look primitive, almost untouched. In plain English, it looked less like a mature galaxy that had plenty of time to grow a black hole, and more like a black hole sitting inside a place that had barely started becoming a galaxy at all. If you are enjoying this so far, pause for a second and hit subscribe, because stories like this are exactly why space never gets old. And if this twist surprised you, send the video to someone who still thinks the universe follows simple rules. Naturally, scientists rush to explain how such objects could exist. One idea is that some black holes were never small to begin with. Instead of forming from dead stars with masses maybe tens or hundreds of times the sun, they could have been born from the direct collapse of enormous gas clouds. If that happened, the starting seed would already be heavy, perhaps tens of thousands or even hundreds of thousands of solar masses. Give that kind of seed a head start, and the timetable becomes less impossible. This is one reason UHZ1 attracted so much attention. Official NASA and Chandra descriptions of the discovery pointed out that its properties fit a long-discussed idea called an outsized black hole, one that may have formed directly from the collapse of a huge cloud of gas. In that scenario, you're not trying to race from a tiny stellar remnant all the way up to a giant in almost no time. You begin the race halfway to the finish line. A second idea is that the speed limit itself may not be as strict as we once thought. Maybe the Eddington limit is a useful average, not an unbreakable rule. In the dense and chaotic centers of the first galaxies, a black hole might feed in short, violent bursts that temporarily outpace the standard limit. If those bursts happen often enough, growth could be much faster than the classic picture allows. This is not a desperate fantasy. It is a serious line of research. The early universe was not calm, gas clouds were thicker, mergers were more common, and environments were more extreme. If there was ever a time when black holes could overeat, it was probably then. But then came the third explanation, and this one changed the argument in a different way. What if some of these black holes only looked impossibly massive because we were measuring them through a disguise? That question became much more important when astronomers began examining little red dots in greater detail. One of the biggest breakthroughs came from a little red dot called Glimpse 17975. Webb captured the deepest spectrum ever taken for one of these objects, and the data contained more than 40 spectral lines. Instead of pointing to a clean, open view of a supermassive black hole, the spectrum suggested something more complicated. The leading interpretation from that 2026 work is known as the black hole star scenario, sometimes shortened to BH star. In this picture, the central engine is still a rapidly feeding black hole, but it is wrapped inside a dense cocoon of partially ionized gas. That cocoon absorbs, reshapes, and scatters the light pouring out from near the black hole. It can also hide much of the X-ray emission that astronomers would normally expect to see. That matters because, for a while, little red dots had a strange personality. Their optical and infrared signatures often hinted at active black holes, yet many were faint in X-rays. The cocoon model gives a simple reason. The X-rays are not necessarily absent because the black hole is weak. They may be buried. Even more important, the cocoon changes how scientists read the broad lines in the spectrum. If you assume those broad lines are caused mostly by gas racing around the black hole at extreme speed, you infer a very large mass. But if much of the broadening is actually caused by electron scattering in a thick cloud of gas, then the true motions are slower than they appear, and the black hole is smaller than first believed. That is exactly what one major 2026 Nature study argued. After accounting for electron scattering, the intrinsic line cores became much narrower, and the inferred black hole masses dropped by about a factor of 100. Instead of needing monsters with masses wildly out of scale with their galaxies, many little red dots could be explained as young, lower mass black holes in the range of about 100,000 to 10 million solar masses, accreting near the Eddington limit and buried in thick gas. That is a huge shift. It means at least some of the supposed crisis may have been a measurement problem, not a cosmic one. And yet, this does not make the mystery disappear, because the universe did not hand astronomers one single clean answer. It handed them layers. Some little red dots may indeed be lower mass black holes wearing thick gas cocoons. Some may still be genuinely oversized. Some may represent black holes caught in rare phases of violent growth. And some, like QSO1, have now produced evidence that is harder to wave away because the mass was measured directly from the motion of gas, not only guessed from broadened spectral lines. Then there is UHZ1, the object that kicked much of this discussion into high gear. UHZ1 is awkward in a special way. Its mass estimate did not come from the same kind of spectral broadening analysis that the cocoon model corrected for many little red dots. Its mass was tied to X-ray observations from Chandra, combined with Webb's view of the galaxy and the lensing magnification. In other words, the new work that softens the case for some little red dots does not automatically rescue us from UHC1, so the tension remains. Maybe part of the early black hole crisis is easing, but part of it is still standing there, arms crossed, refusing to move. And that is what makes this such a great science story. The answer is not simply, we were right or we were wrong. The answer may be that the early universe had more than one path to making black holes, and we are only now learning how to tell those paths apart. Around this point, the biggest question becomes almost philosophical. What exactly are we watching when we look that far back? Are we seeing the first black holes grow into galaxies? Are we seeing galaxies feed black holes? Are we seeing measurement tricks caused by extreme environments unlike anything near us today? Or are we seeing all of these at once? Here's the emotional weight of it. We are not looking at the universe in its comfort zone. We are looking at it when it was young, unstable, improvised, and still making up the rules of its adult life. The light from these objects has traveled for over 13 billion years. It crossed expanding space, survived collisions with dust, and been around massive structures before hitting our detectors. We are trying to reconstruct a crime scene from a few ancient photons. It should not surprise us that the first draft of the story was messy. Still, there are facts that refuse to lose their force. UHZ1 appears only 470 million years after the Big Bang, and may contain a black hole weighing between 10 million and 100 million suns. Its black hole may be as massive as all the stars in its host galaxy combined. QSO1, seen around 700 million years after the Big Bang, shows a direct black hole mass of about 50 million suns, and a central object that may hold about 2/3 of the system's mass. Cannick's LRD Z8.6, observed just 570 million years after the Big Bang, adds another case where a compact early galaxy hosts a black hole growing faster than expected. Even if half the little red dots turn out to be smaller than first feared, these remaining objects are enough to keep the field honest. They force astronomers to ask harder questions about how structure formed in the first billion years. And those questions reach deeper than black holes alone. Because if black holes formed earlier and heavier than expected, they may have shaped the birth of galaxies themselves. A feeding black hole releases enormous energy. It can heat gas, blow matter outward, and regulate future star formation. That means black holes are not just passengers sitting quietly at galactic centers. They can be engines that influence what a galaxy becomes. So imagine the early universe not as a calm nursery, but as a contest between gravity and light. Gas wants to collapse. Radiation wants to push back. Stars want to form. Black holes want to feed. Galaxies want to assemble. And in some rare places, one player may have surged ahead far earlier than the others. Maybe that is what Webb is catching. Not a violation of physics, but a violent shortcut written into physics under conditions we have barely explored. If this part of the story has you thinking differently about the cosmos, drop a like now and share this video with the one person you know who asks the best questions. And if you want more deep space mysteries explained simply, make sure you're subscribed before we reach the ending. There's also something beautifully humbling about how fast this debate has moved. Little red dots were only noticed after Webb began science observations in 2022. In just a few years, they went from faint red smudges to one of the most argued over populations. That is an unusually fast correction cycle for science, and it shows what happens when a new instrument reveals territory no one had seen clearly before. In one phase, these objects looked like evidence that cosmology itself might be in trouble. Then, deeper data suggested dense gas cocoons could explain many of them. Then, direct measurements on at least one extreme object pushed the problem back onto the table. This is not weakness. This is science under pressure. Hypotheses rise, collide, and get cut apart by better evidence. That process matters because it protects us from a seductive mistake. The universe is under no obligation to be simple, just because simple stories are satisfying. Webb was not built to protect our expectations. It was built to test them, and that is exactly what it is doing. The telescope was supposed to help show us the dawn of galaxies, the first generations of stars, the slow buildup of structure after the Big Bang. It is doing that. But mixed in with those answers are objects that feel almost rude in their timing. Black holes that seem too massive too soon, galaxies that look too small for what they host, spectra that imitate one thing while hiding another. Every one of those details pushes us toward a more mature view of the early universe. Maybe there was no single neat ladder from star to seed to giant black hole. Maybe there were several routes, direct collapse for some, extreme feeding bursts for others, dense cocoons that fooled our first estimates in many cases. And perhaps even more exotic possibilities still waiting in the dark. This is why gravitational lensing has become such a quiet hero in the story. Without these cosmic magnifying glasses, some of the most important early black holes would remain invisible. Abel 2744 helped reveal UHZ1. Lensing also made detailed work on QSO1 possible. Somewhere out there, other galaxy clusters may be bending light from even stranger objects toward us right now, objects that could either calm this debate or blow it open again. Future observations will matter enormously. More Webb time, more deep spectroscopy, better X-ray sensitivity, more lens targets, more direct measurements. Every new data point will help sort objects into categories instead of one mystery. That sorting is everything, because when people say Webb found massive black holes too early, that sentence is true in spirit, but the details now matter more than ever. Which black holes? Measured how? In what environment? Hidden by how much gas? Magnified by what factor? Fed at what rate? The next decade of astronomy may be about turning that one dramatic headline into a map. And there is another reason this matters. The first billion years of cosmic history set the stage for everything that comes later. If black holes were already huge during that era, they may have influenced where stars formed, how gas moved, and which galaxies stayed small or became giants. A black hole is not just a hole, it is a machine for shaping its surroundings. It can heat gas, launch outflows, and decide whether future stars get the fuel they need. So when astronomers argue about early black holes, they're really arguing about the architecture of the young universe itself. And maybe the biggest emotional turn in this whole story is that uncertainty is not a disappointment. It is the prize. If Webb had simply confirmed every expectation, the universe would feel smaller tonight, more orderly, more finished. Instead, it handed us a puzzle with missing corners and pieces from different boxes, and somehow that is more thrilling. It means reality still has the power to surprise the best instruments we have ever built. When you hear that Webb detected one of the most massive objects ever seen so early, the real headline is not just size, it is timing. Timing is what gives the discovery its bite. A giant black hole in the modern universe is impressive. A giant black hole in a universe only a few 100 million years old is a challenge thrown directly at our models. That challenge now comes with nuance. Some of the apparent monsters may shrink when we understand their gas better. Some may stay enormous. Some may force us to accept that black holes were born heavy from the start. And some may reveal that galaxies did not always lead the dance. Sometimes the darkness may have taken the first step. So where does that leave us right now? It leaves us with a universe that may have built at least some of its largest engines before it built the structures we expected to contain them. It leaves us with one record-breaking X-ray black hole in UHZ1 that still resists an easy explanation. It leaves us with little red dots that are no longer a single mystery, but a crowd of related ones. And it leaves us with the strong possibility that the early cosmos was more creative, more violent, and more efficient than our older stories allowed. That is why discoveries like this land so hard. They do not merely add one more object to a list. They change the feeling of the era we are looking at. The first billion years after the Big Bang stop feeling like a quiet beginning and start feeling like a frantic race full of hidden giants. And maybe that is the image worth keeping. While the first stars were trying to switch on the lights, while young galaxies were still gathering themselves out of raw gas, somewhere in that deep young darkness, massive black holes may already have been growing with shocking speed, betting the future of whole galaxies around them. We caught one of them only because space itself acted like a lens. We understood part of the picture only because a telescope in infrared and an observatory in X-rays agreed. And even now, after all the excitement, the best answer science can give is still the most honest one. We do not fully know how all of these monsters formed. But we know enough to say this. The early universe was not waiting around. It was building extremes almost immediately. And every time James Webb looks deeper, it seems less like we are calmly reading ancient history, and more like we are overhearing the universe confess that its beginning was stranger than we were taught to imagine.